All right, so now that we have gone over processing samples, we are going to get started with how to use these extended parameters in begin analysis and just show some examples of ways to potentially use different parameters to improve sample quality or to support your analysis. The very first steps that we have to do are our quality control steps. And so I'm just going to show this with 3 histograms. You can definitely speed this up with combining some of these into a dot plot. But just for clarity, I'm going to demonstrate each parameter. So once the sample's been processed, we get these 5 separate categories of extended parameters. We have our shape, intensity, pixel, object feature. This is our particle count, or this will be our singlet count, and our system features. These are going to help us with the quality control steps. So system features, the 2 that we are going to want to focus on is on border and is processed. And the entire goal here is to make sure that we have excluded any events that have not been fully imaged, which would lead to incorrect values for area, perimeter, and other calculations, and that we want to make sure that we are only working with processed imaged events. So events that have an image attached, which is actually processable. So it is not just noise, and it was successfully processed. So all I'm doing over here in the Customize tab is I am just changing the min and max range of the scale so we can all see it a little better. And let's start over here with is on border. So think of this as a binary question. So is it on the border, yes or no? So if we come over here to the image view gallery and we just look, most of these are on the border. I can turn the masks on so we can see. And if I come over here, these are not on the border. So we are going to go ahead and use these. So not on border. And then down here, that will be our new parent gate. So not on border. And we are going to say is processed, yes. Say imaged and processed. And set this to black. Up here in edit gates, I can also turn off all back gating if I want and delete a gate that I accidentally set incorrectly. So now imaged and processed is going to be our parent gate. And if you're wondering why this is so many of these events don't have images, and let me just show you really quick. That's because the image capture settings were set up to image every 10th event, and I could verify that here in the image capture settings tab. So at this stage of the quality control workflow, this looks exactly the way I would expect. I don't see any issues. Remember, we have already done the image quality control of the masking and spot count. So if I come over here, now we're going to image processed, and this is where we are going to set our singlet gate using the particle count feature. So the first thing that I've done is I've set the image and processed gate as my parent gate, and then I'm just going to go to object feature particle count. You can see I have singlets, doublets, and then the aggregates. If we come in here, this is a very accurate feature and more or less universally applicable to any workflows where you are assessing singlets. In an immunological sample, it is much more accurate than manual gating. And as you can see, these are all the singlets within this gate. This was validated on leukocytes that, within an error or with an error rate within 10%. So this is an extremely accurate tool to use when you are trying to ensure that you're only working with singlet events. So here, the doublets I'm going to exclude for now. And we're just going to have our singlets, but I'm also going to set a doublet gate because some of the parameters we'll look at are very useful for anything that is a doublet. And so at this stage, I have excluded any events that were not fully imaged, so any events off the border of the image. I've only included processed images in my subsequent analysis steps, and I've also done my singlet and my doublet gating. And this is where a lot of people start to get hung up on what parameters are best to start with and how to begin applying them. There's a couple different ways to do this, but one of the most useful ways, if you really are unsure which ones just to begin applying, are to just look for some resolution on histograms between different parameters. So if I was going to look for a potential parameter to use analyzing the sample, I would set my gate, and I would come in here and potentially compare entropy intensity. And this is a great example of that resolution versus, let's say I was interested in kurtosis. See this, I'm not seeing the same clear resolution between populations, so I may not focus on this parameter quite as closely. We can see this with standard deviation versus skewness. However, one of the things that I can do is use a parameter that gives me really good resolution and plot that against one of these parameters where I'm not seeing the same clear delineation. So coming in here, skewness and CV norm intensity. See, now I'm starting to get this separation. And one of the things that we know about our sample is that the beads are probably going to be more highly skewed than the cells because they are so much darker, so the pixels are so much less intense, less bright. So looking here, let's look at R3. And there we have it. You know, these are mostly beads. And let's look at R1. Those are mostly our bead populations. And so this is one of the ways that I would begin to potentially backgate onto this plot. So you see I'm taking this plot, turning it into a dot plot. And I am going to make this much brighter. It's the resolution. And you can see here, this is my bead population during acquisition. And if we look over here, my guess is these are debris, cells on beads, because they're at the midway point between the majority of the population and the beads. And let me turn the masks off to show you. And here we go. Cells and beads, or cells and debris attached to beads. As you can see, this is spread throughout the sample. Almost every event in here is attached to a bead, so that means that most of these events here include a bead in the majority of the sample. And so then this population down here is going to be our cells and debris, dead and dying events. And we know that that's actually, you know, this is the group that we're more interested in resolving and in removing the debris and dead and dying events for a final cell count. So I'm just going to name these really quickly because these give us a really good opportunity to use some of these other parameters. I'm actually going to switch to the doublet gate. And let me change that resolution. The reason I'm doing that is because I want to demonstrate a way to use a particular feature, eccentricity percent, to potentially call out some of these events that are coincidental. So there's simply two of them imaged in the same field versus actually interacting. And eccentricity is a really helpful way to do that. And so if we come up here, and I'm just going to show you on this plot before we look at our actual cells and beads population. The high eccentricity percent shows us events that are not interacting. Whereas as we move lower, below 75, we start to see more of these events that are actually connected and have some kind of interaction going on. And we're going to see our beads and cell population. There we go. Our beads and cell population here below 50, between the 50 and 25. And so this is a very useful parameter to call out interactions versus coincidental events. And if we switch this to cells on beads, we can see here they're attached. Whereas if we come up here, these are unattached and are simply coincidental. There's mix there, and then as we come down, see the same thing. So one of the other useful things, or another one of these useful size parameters is circularity, and this is very useful for cell health. So let's go ahead and let's look at this population. So if I come to shape features and circularity, I know for the most part that everything below around 80 is going to be debris and dead and dying cells. And so as a general rule, with a lot of my dissociations and really messy samples, I'll gate out anything below 80% circularity, just as a general rule of thumb to help clean up my sample. So if I look here, and you can see 72 to 80, that's my range. If I go up a little bit, we're starting to lose some of those cells and debris. I might actually gate everything out below 85 in this sample because it is so messy. But it's up to you depending on what you are trying to assess with your sample. So if this was mine, I would just say everything below 85 can go, and I would set my lower threshold at 85 and only go forward using this sample of cells. And so actually let me call these circular cells. So that's a very useful parameter. And so if we come in here and we, let's say, just add a density plot with circular cells, we have a much cleaner plot, and we can begin to look at these in the same format as some of these others. So CV, -2 to 2. This is 0 to 150. And we can see how much we've cleaned that up to compare. And so what I would definitely caution against is using any of these as hard and fast rules. This really is sample dependent. It depends on your analysis goals. But there are a lot of ways these parameters can be used to help clean up a messy sample, to improve the downstream analysis that you would be able to do, to verify that you are working with particular populations, and especially to really tease out the nuance between the coincidental events, the interactions, and overall improve the level of resolution that you can achieve. So the last thing that we can look at here is on these dot plots. What I'm going to do is change this to imaged dot plot, and then I'm just going to turn off all the back gates except beads, cells and beads, and then the R4 gate, which is my which is just the cells. And so here, let's make this purple. And let's just see where everything is. So here we have beads. Here we have cells and beads, which are taking up the whole plot. And this is the cells and debris versus just the circular cells. So that's kind of the distribution based on these parameters within this sample, which is, again, uniquely messy compared to some of the other immunological samples that you will probably want to run.